All right, welcome to lecture two of our So today we're going to be talking about imitation learning. But to start, let's think about some logistics. So we're going to have paper readings, I think, the week after next. And so I'll send out an email with randomly assigned roles for the next one with the description of what you need to do. And so maybe you guys should get together and see if you could discuss the paper. And I'll post those things maybe tomorrow or day after. But they'll be regarding model-free reinforcement learning and imitation learning. And also you should start thinking about your final projects. We'll have a project milestone in like 2 weeks or so, like where you just propose an initial project. And so start thinking about it, form teams. If you need help forming teams, let me know. The other logistical thing is I am asked to be in the Bay Area this Tuesday to get money. I will do the lecture remotely, and the TAs will run a PyTorch tutorial for those of you who aren't familiar. And so they'll do half a PyTorch tutorial and half I will do the lecture remotely. You're welcome to skip it if you're already familiar, but that's what Tuesday's lecture will be. So half on PyTorch and half on policy grading. Okay. So we only got through half our lecture on Tuesday, so we're going to try and get through the rest of it in an abridged fashion. So we'll talk a little more formalism, why we should care, and see more about whether RL is the right paradigm for decision making. And then we'll start diving into a simple paradigm called imitation learning. So we'll define some preliminaries, talk about this algorithm called behavior cloning, which a lot of you might have heard about, and then talk about two fundamental problems in behavior cloning. The first being multimodality, right? When people are trying to demonstrate different strategies, behavior cloning tends to fail. And the second is compounding, right? So we'll talk about behavior cloning and what's wrong with it, how we can fix it. Yeah, any questions before we start?
Can you lower the
Yeah, there's more. Alrighty. So, if you recall, last time we talked about this framework for reinforcement learning called the Markov decision process, where we have states, actions, rewards, transition dynamics, an initial state distribution as discount factor. And the key part about an MDP is the Markov property. And so the future is independent of the past condition of the present. And using this, we defined an objective, which looks like trying to maximize the expected sum of rewards under a policy, right? Where a policy is a mapping from your state to a distribution over action, right? And so we said we have a stochastic policy, stochastic environment. You want to maximize the expected sum of rewards when you sample trajectories from your policy, right? And so that is the objective. And we really want to use experience in the environment to infer the parameters of our policy theta or pi theta. And theta can be linear functions, tabular functions, neural nets, right? It's an arbitrary function approximator. This all ring a bell? Seems reasonable? Okay. So the place we stopped at last time was trying to unpack this expectation, right? So we talked about how there's a trajectory view on this, where you have ancestral sampling, starting at an initial state, sampling actions, next state, actions, next state, actions, next state, right? So you sample things sequentially. And then we talked about the view of this, which is from a stationary distribution. So stationary distribution is kind of like in a Markov chain. When you run your Markov chain for long enough, it converges to a stationary distribution. It's the analog of that when you have an infinite horizon MDP. The stationary distribution is the analog of that when you run a policy for long enough in an MDP. It's the distribution that your state actions converge. And so you can re-express this sum of rewards objective as the expected reward when states and actions are samples from the stationary distribution you find again. And so we don't have to get into this until much later, but the way you want to think about this, I think this view is much easier to think about. It just saying you sample states and actions sequentially. You want to maximize the sum of rewards. And this view is trying to say when you sample states and actions directly from the stationary distribution of your policy, you want to maximize the rewards, the expected rewards, right? And these two are equivalent for an infinite horizon discounted. Any questions here before we move on? Yeah.
where does the new thing get derived from? Is it from the top or then?
Yeah, and it basically just take this thing and then you just sum it up over all possible factors. So
That's
this
what
is,
seem like to try to get to the.
oh, like this showing that this thing, you can show that basically, like this thing can be re-expressed as these two things are equivalent. And it's like when you have like, like one way you can think about it, if you take a Markov chain, like the top thing is like starting from an initial state, just like sampling through the Markov chain. And the bottom thing is like, instead of like sampling through the whole Markov chain sequentially, you just like sample from the stationary distribution. And the way you equate them is just by like, the stationarity of a normal mark. This is the safety.
There's assumed that some learning theory.
Yes, yes, exactly. Because it's infinitarized. That's the whole point.
Yeah.
It's that. Okay, so the things we didn't get to are things that are going to be super important, right? So there's notion of Q functions and value functions. And so you can think of a value function as basically saying, so this typo, it should be V by S. But V by S is basically starting at some particular state S. If you continue executing a policy phi, so if your initial state is S and you execute a policy phi, what is the expected sum of the words from that state S? You follow policy phi under the system dynamics, right? So it's pretty similar to what we had before, but it's just starting from a particular initial state, right? So the value function is essentially trying to evaluate how good is the policy phi when you started from an initial state S, right? And so that's what your value function is. Make sense? Yeah. That's a typo. Right? Oh, yeah. I will fix that. Let me make a note to fix that. Yeah, I'll fix that in the slides. And a Q function actually has an A, so that's not a typo, but a Q function is similar to a value function, but it's saying that take start at state S, have the first action be A, and then follow the policy thereafter, right? And so it's saying like it's the value of the particular action A when taken at S, and you follow the policy phi thereafter. And so we're going to use this definition of a Q function to find a way to improve policy in the future. But you can think of it as telling you how good action A is at a state S. Right? And this thing is telling you how good a policy phi is at a state S. So the difference here is that this is like conditional. The first action is like A, and here the first action is taken from phi. Yeah, so that's the main difference. So given this definition, can someone tell me how V and Q are connected? Yeah.
The value function is essentially averaging over all the actions of a Q function at like some state. So it's like
Perfect. Right. So the value function is the expected Q function when the actions are sampled from the policy file. Right. So you can think about it. The way you can think about it is the Q function is starting at state S, taking action A, and then following the policy file. The value function is kind of doing the same thing, but at the first step, it's always acting according to policy phi, right? So you can say that the value function P5 and typo is equal to the expected Q function, where the first action is sampled from your policy, right? So whenever you see a value function and a Q function, they're like inherently connected. Right? Now, sometimes you'll see like V stars and Q stars and these kinds of things. You'll get to those. Those are like optimal value functions and optimal Q functions. But the whole point of having these value functions and Q functions is that they let you evaluate how good a policy is. And if you can evaluate how good a policy is, then you can do ascent on that objective. So you can say, let's make the policy better. And so what we're going to do with these value functions and Q functions is try to define like an ascent objective where we make our value functions better or our policies better using the value functions to evaluate how good they are. So you usually go between a step of policy evaluation, which says for a particular policy, try to understand how good the value is, right? And policy improvement, which says try to do ascent on that objective to make the policy better. Yeah. So don't worry about the details right now. We'll get to it in a second. But the way you like evaluate a policy typically is that you're going to define this entity J, and the J is just the expected value function where states are sampled from your initial state distribution, right? So it's saying V5 of S is telling you how good is the policy from some state S, and how good is a particular policy is the average of the value function over states from your initial state distribution. Right? So it's saying like the value function says starting from this S, how good is the policy, and how good is the policy in in total we want to average this over all the initial states that you have. And so this is typically the objective you want to maximize. You want to maximize something which looks like J5. And J5 is exactly the same as the objective we had in the previous slide. They're saying how good is your policy when you start from your initial state distribution and then keep rolling on. Yeah. So, yeah.
Is there no discounting factor here?
Oh, yeah, there can be a discounting factor depending if you're finite horizon or not. Right? So it's like, as I mentioned last time, I'm like a little sloppy with discounting factor just to be simpler with notation, but you could make this like, you could have gamma to the d. Good question. Any other questions before we keep going? So we're not going to touch Q functions and value functions for a while, for like at least 2 more lectures, but it's good to know. Okay. So a natural question to ask is, you know, a lot of you have taken machine learning classes. Is this just supervised learning, right? And so typically in supervised learning, someone's going to give you examples of success, right? It's going to give you examples of XY pairs, which are optimal, right? Or SA pairs that are optimal. And then you're going to try and maximize the likelihood of an optimal Y given an optimal X, or given some X, right? So you're going to be given like typically in image classification, you're going to be given images as your X and labels of cats or dogs or airplanes as your Y. And you want to maximize the likelihood of that label Y being produced by your model P hat theta, right? And so you're going to say that when you take expectation of X and Y sample from your data set, you want to maximize the log likelihood of the label Y being produced under the input X, right? So this is just maximum likelihood. And the important thing to note is that your expectation is not done under your model, your expectation is done under your data set. So X and Y sample from D. So we're going to assume that in supervised learning, you always assume it's optimal. It doesn't make sense to copy something that's not optimal. And so this is what you typically do in maximum likelihood. Now, why is this not just supervised learning? Why is RL not supervised? What's different? There's no static data set. And so supervised learning is saying the static data set, you want to maximize the likelihood of Y given X. RL is saying that you're sampling your data essentially from your policy phi theta, right? And then you're trying to maximize the notion of the word. And so the difference here is that in RL, your expectation is under phi theta. And in supervised learning, your phi theta is inside the expectation, but your expectation is static, right? And so what that means intuitively is that in reinforcement learning, your data distribution is controlled by the thing you're trying to learn. Whereas in supervised learning, the data distribution is fixed, right? And so like you can think of this as like you're trying to change the thing that collects the data, not just the thing that does prediction of the data. And so if you like kind of think of this from how many of you know what KL divergences are? Good. Okay. If you think of this from the perspective of KL divergence, you can think of supervised learning as a forward KL divergence between P star and P theta, where P star is an expert and P theta is the model being learned. And you can think of RL as the reverse KL divergence between P theta and P star. We won't go into I'll go into the derivation a bit more in imitation learning, but just think about it intuitively. It's like this one is saying you're trying to sample from P star and then try to match P theta. And this one is trying to say you're trying to sample from P theta and match P star. Right? And so it just matters where you're collecting the data from. And that's going to make an impact because like in practice, you're not going to have a static data set. You're going to have the robot collecting its own data. And so reinforcement learning is useful in settings where you like need to have the robot deployed sequentially. Whereas supervised learning is great for like one-step settings, but not great for multi-step settings. And we'll talk about why in a lot more detail. But does this kind of make sense intuitively? Any questions? Okay, good. Okay, so there's this difference we mentioned in the expectations. And that actually results in like a lot of practical differences. Like supervised learning is far easier to stabilize. Doesn't like if you look at RL learning curves, they're like on up and down and up and down, and there's huge variance, whereas supervised learning is always like pretty stable. And because you have to collect your own data, often you have this balance between exploration and exploitation. Whereas here you're not collecting your own data, right? So there's no exploration. Here you have to collect your own data, so it matters what data you collect, and so often there's a balance between how much you explore versus how much you exploit, and these considerations don't exist in supervised learning. So that's what makes it harder. But what a lot of modern RL tries to do is try to take RL and convert it into as close, convert it into supervised learning as much as possible, right? So it tries to like do some version of iterative supervised learning as much as it can to kill like a lot of these things called offline RL, etc., are like trying to do some version of supervised learning or supervised learning type things. Okay? And so the only thing I trust in life really is supervised learning. So if you can convert problems into supervised learning, your life will be better. Okay, so why should we care about RL? Well, one is that it's particularly well suited to solving sequential decision-making problems. Right? If you're solving a one-step decision-making problem, with supervised learning is fine, right? But when you're talking about a sequential decision-making problem, your decisions affect your future decisions, right? And so RL is able to like, is a better framework to tackle those kinds of problems. So it's good for sequential decision-making. In principle, it should enable continual improvement. You don't usually assume things like gradients and so on from your simulator, right? Which makes it, more applicable in things like trajectory optimization in many cases. And it reduces the burden of human data collection, right? So you don't have to like have someone like put on gloves and pick up things, right? So it comes with other costs, but in principle, these things should hold. And we'll talk about how some of them hold and some of them don't hold. But that's why we should care. Or that's why I think we should. Any other thoughts on why we should care about this? Because you don't have to like structure your environment in particular. Right? Like the real world is the real world, and I can't like force everything to be differential, or I can't force everything to be smooth. That's just like not how the world will work. So in certain cases, like there's a trade-off, as in like the less assumptions you have, the more inefficient your method's going to be. But for problems in the real world, like if you're trying to like stack dishes, unclear how you'd model it in a smooth differentiable content model. Okay. All right. So we've talked a little bit about the applications. So here's some that I find compelling. So we have robotics, of course. But recently LLMs have been an interesting application for RL, mostly for the purpose of reducing hallucination. And so the goal here is that if you train a model with supervised learning, when you feed it in new inputs, it can hallucinate. And they try to train reward models that can identify when models are hallucinating or not, and then try to like probe a model for hallucination and push them down. So the way I think about RL in that setting is like whack-a-mole. Like you have different hallucinations. And if your reward model is generalizing, you just push down all the hallucinations. You don't have to use RL. There's a lot of stuff that's trying to get rid of RL, but RL is an effective solution. Things like games are particularly well suited because you can reset, you get rewards, you can collect tons of data, you can parallelize, you can go at 100x real-time speed, right? And so you tend to do really well, especially in multi-agent games. And lastly, I think there's like some cool work recently on using RL for chip design, for engineering design. People have tried to like formulate chemical design as like a sequential decision-making problem where your actions are placing different molecules in different places. I wouldn't say I'm an expert on that, but I think it's cool. Right. So one of you should do it for your final project and extra credits. So useful thing to think about is where is reinforcement learning not useful, right? So we've talked about where it is useful, but RL is not really useful in applications that are safety critical or repetitive, right? So if you have things like assembling things in a factory, do motion planning. Don't waste your time with RL. It's like a silly thing to do. If you have things where you have like extremely safety critical maneuvers, like the guarantees, especially with deep RL, are like weak to non-existent. And so those applications are not great because you don't really get guarantees out of it. Or things like surgery, I don't know if you should do RL. I think those things are tough. And so I think RL is great when the cost of failure is not that high. And so you have like a little dog walking around and it falls over once, it's fine. But if you have someone doing surgery, I wouldn't do RL for that, at least personally. Yeah. That's a bad idea. I don't think they did it for a real reactor. I think they did it conceptually. But yeah, I wouldn't do it first. if I was there. Cool. So a natural question to ask is, okay, we've talked about RL as a technique for sequential decision making. Is all sequential decision making just RL? But RL is really sequential decision making under a particular set of assumptions, right? So you're assuming that you can sample from the environment, you're assuming that you have access to a reward, you're assuming that you have like a particular goal that you want to solve, right? You have a reward. And it's not clear that those assumptions hold. So what are other things that might be useful for sequential decision making that maybe violate some of these assumptions? Any thoughts? So RL is one where you say, okay, if there's an environment, you have only sampling access to the environment, you get a reward, and you're trying to solve a single task. What are other things we can do to do decision making in sequential sense? Or is RL the one to do?
Enable demonstrations.
We have demonstrations. That's I don't know how to skip my next transition, but yeah, we'll get back to it. Are there other things you can do? So maybe in cases where you say don't have access to reward, it's great to assume you have access to demonstrations, but no reward. That'll get away. Are there other things you can do? Like preferences kind of? Yeah, preferences totally makes sense. Often what people do is they take preferences and convert it into a scalar value thing, but you don't have to. Yeah, it's a good one. The other things, so things you can do is like, like you were saying, are black box assumptions good? Probably not in all cases, right? So in cases where you do have access to like some sort of a model, you can do things that are much more efficient and much more performant, and search is easier. So just the way I think about trajectory optimization or planning is it's like RL with more assumptions on the model, right? Or RL type things with more assumptions on the model, which allows you to do more efficient, more performance things with more guarantees, right? So in cases where you do have access to more than just sampling from the environment, right? You can assume access to gradients, you can assume access to like a resettable simulator. You should use things like trajectory optimization or planning.
Is limited to relatively.
When you have things that are imitation learning, right? So let's say you like had someone provide you demonstrations. So this is from PRI, and so we have someone collecting demonstrations in this environment. So you don't need reward, you just need some number of demonstrations, and so it lets you get away from this like reward access that makes RL hard. It comes with its own set of problems that we'll talk about today. But another paradigm is imitation learning, which is reasonable. Right? And then lastly, you might have like unsupervised decision making. So you just like collect a bunch of data in the environment, right? You just have a robot just fucking around in the environment and collect a bunch of data. You can learn how the world works so that you can then make directed decisions after that, right? So it's often called unsupervised RL, or some people like to call it world modeling, and some people like to call it model-based RL, right? A lot of it is like, how do we collect data without a particular task in mind, learn how the world works so that you can then do goal-directed behavior. Right, so I think these are some ways of doing it. There's lots of others, but I find these ones to be particularly interesting.
Where the robot has
So we'll skip some of the details. Let's take a shot.
is limited to
But I'll show
is
you the
limited-
videos in a few minutes. Okay, so we've talked about RL, the paradigm. We've talked about a few alternatives to RL. So we've talked about trajectory optimization, we've talked about imitation learning, unsupervised decision making, unsupervised RL. But let's think about what makes an effective RL, right? So the first thing you need is like stable performant optimization methods. Right? So you want a method that's able to like optimize that objective that we talked about, do it in a stable and efficient way, right? You need objectives that are easy to specify. A lot of these things are assuming that you have a reward. Where does the reward come from? You have to make it up. So you need ways to specify objectives and rewards clearly. Lastly, you need to think about exploration and try to make this whole process efficient enough to be practiced, right? And so the design of any reinforcement learning method kind of needs to like deal with these issues. And so a lot of the RL algorithm work kind of focuses purely on this, but I think it's equally important to focus on both. And so the way we're going to structure our whole class is we're going to start with imitation learning, which is the simplest, silliest thing you can do. Then we'll talk about model-free RL. We'll talk about policy gradients and approximate dynamic programming. We'll then talk about model-based reinforcement learning, right? So model-free reinforcement learning is trying to use trial and error to learn a policy. Model-based reinforcement learning is trying to learn an approximate model of how the world works, an approximate model of transition dynamics. We use that to learn a policy. We'll then try to provide a unifying perspective on this through variational inference and some ideas from that. And then we'll talk about frontiers. So like, how do we make this thing practical, right? So we'll talk about things like exploration, learning from prior data, learning across tasks, generalization. So that's how we're going to structure our class. Unless you speak up now and make me make a difference. And so if there's other things you'd like to see, let me know. I am making the lectures on the fly. And so you can change those things. Okay. So are we ready to get into imitation learning in some detail? Great, let's do it. Okay, so that's MDP formalism, why we should care in our classroom. So let's start by thinking about imitation learning. So imitation learning goes, this is an example I stole from my my student Kate. But basically it's this person learning how to do Gangnam Style from side. And I thought that was interesting because it like demonstrates a somewhat complicated coordination behavior. And a lot of like what people do watching their parents or other people is through imitation. And so the paradigm of learning through imitation is intuitively very appealing, and like a lot of psychology is focused on that. And so we'll try and actualize that into a real algorithm today. Right? And so the setting we're going to go with is we're going to have demonstrations of optimal behavior. So let's assume that we have trajectories, right? So S naught I, A naught I, S1 I, A1 I, so STI, ATI. Let's assume it's finite horizon for now. And let's assume that you just have n of these trajectories. Right? And so you have a set of demonstrations of optimal behavior. And what we want to do from this optimal behavior is train a policy that's able to mimic the demonstration. So we want to learn the parameters of a policy phi theta A given S that mimics the demonstration. And so notice, unlike reinforcement learning, we're not going to assume access to reward. This is all that you, right? You just have environment. You just have transitions from an expert, and you want to learn an optimal policy phi theta, right? And we're going to assume that the demonstrations are optimal or close to optimal. Right? So we're not going to try and do better than the demonstration. We're just going to match the demonstration. Right. And so what we're going to try and do is we're going to try and operate in the setting where we don't have rewards. And also let's start by thinking about settings where we don't require online experience, right? So you're just given the set of offline data. You just want to learn a policy, and you don't want to assume access to the simulator or the environment until you have to deploy your policy. Right? So no online experience needed. We'll talk about, this is not the only way to do imitation learning. You can do imitation learning with access to the environment. But we'll talk about that in a later class. Yeah. So this is a setting we care about. Offline data, optimal. We want to learn phi theta A given S. Okay, how do we do it? What's the strategy? Supervised learning. Great. So what we're going to do is we're going to we're just going to treat imitation learning as a supervised learning problem, right? So we're just going to say we took our optimal state action pairs, right? And then we're just going to do supervised learning, which says that we're just going to say treat S star as X and A star as Y, right? And you just want to maximize the likelihood of A star being produced when you have S star as input to your policy. Yeah.
I don't quite get the setting of the data set, right? Because if you already have the optimal pairs,
yeah,
why are we using it?
Because you have one is you have stochastic environment, right? So you're never in the same thing. So you're never guaranteed that the same transition holds. Secondly, you might never be in the same state again, right? Because you're in a continuous environment. So you want to learn a function approximator that works in another setting. Now, if you're in a tabular setting, you don't need this, right? So the whole point is that because you have function approximation, like if you had a car, you're never in exactly the same setting. So you want to learn a policy that generalizes.
But you've discretized the states, right?
No, we haven't discretized. Okay. Nowhere have we discretized it, right? So the states are continuous. Yeah, states and actions are both continuous. Any other questions?
Do they be continuous?
They can be, they cannot be. But if the states are discrete, then you don't need this, as you were saying. Yeah, good question. Okay, so we're going to treat imitation learning as a supervised learning problem. So we did a few different things here, right? We took the sequential data set, we took our like trajectories, And then we just broke them up into state action tuples, and we treated them as like IID state action tuples, right? So we're just saying that there's a whole trajectory of states and actions, S star and A star, right? Or going back to our definition, we had like a series of trajectories, right? Each of them is a state, and an optimal action state, optimal action state, optimal action state. We're gonna like throw away the sequential nature of the problem. Just take each of these state action tuples, mix them all together into an IID data set, then treat it like a classification or regression problem. Right? So you're like throwing away the sequential nature of your problem, you're treating it as IID. And then notice differently than RL, your expectation is under your data set, not under your policy. Yeah. So what we like the way you would actually implement this is very simple. It's just see. The way you would implement this is you just it's like 20 lines. Don't copy this for your homework. But the way you implement this is very simple, which is basically just saying that there's just a standard supervised learning, right? So you're just gonna say, let's sample states and actions from your data set, right? They have a policy, you stick in the state to your policy, you get a distribution over actions, right? And then you try to maximize the likelihood of the expert action when you feed in the experts. You treat it as IID, you just do like stochastic gradient descent. That's it, like this is the whole code. Right? And Figure just got $2.6 billion to do this. So good. Good stuff. No, I think there's lots of interesting stuff about this, right? But it's extremely simple. You just treat this as like a purely supervised learning. Okay. So going back a few steps, why would we want to do this, right? The pros of doing this is that it avoids the needs for things like rewards or exploration. You don't have to do expensive data collection in the environment. You don't have to like worry about task specification. You're already showing them what you want. The cons here is that you need expert data, which can be expensive, right? It doesn't guarantee that you can get better than the expert or you get better on deployment. And we'll show that it struggles on longer horizon problems. And it's naturally gonna accumulate error. Okay, so what have we done? We've said we have this expert data, state, action, state, action, state, action. We're gonna jumble them all together, treat it as an imitation, treat it as a supervised learning problem, right? Treat it as an IID supervised learning problem, just like image classification or regression. And so we talked about how this is just this code, right? We just want to do stochastic gradient descent of this. Great. And so depending on what type of function approximator you have, you can just do gradient descent through this. And the tabular, it's just going to be like counting, essentially, like we're talking about. With an arbitrary function approximator like a neural net, it's going to be back propagation, right? So you can use arbitrary methods to do this, but you're always going to try and do gradient descent of that objective, parameterizing by theta, whichever way. Okay, great. So this is nice, and this actually works really well in certain cases. So this is from 1989. It's called Alvin. They're trying to get this vehicle to navigate around the forest. It's actually using a 1-layer, 2-layer perceptron with this like simple grayscale image, and they're trying to get it to like lane follow, right? And they were just basically using the same algorithm, just doing supervised learning. So this is from Romerlo. And what are we doing in 2024? We're doing the same algorithm, and it works super well. And we just use transformers and diffusion policies now, but the results are strikingly good, right? And so I think there's something to be thought about there. And so that is the demonstration here, and that is autonomous research. So yeah, it's somewhat convincing that it works so well. That's worth thinking about why so. They struggle on longer horizon problems, and we'll talk about it. All right, so yeah, there's some caveats here. There's not like a tremendous amount of generalization here, and there's obviously problems like embodiment shift. So the reason they're wearing these gloves is to deal with embodiment shift, so they don't want to have the hands in the video and so on. Yeah, it's seems like the motion wants to. Yeah, so I think what they're doing is they're keeping it almost quasi-static, so that you don't accumulate error in the same way. So they like run it through a low-level PID controller, and they keep it almost quasi-static so that it uses feedback to throw the stability. So that's why it's so slow. Okay, so this works really well. This is great work from Sharon and friends at Stanford, but we'll talk about why this might not be the entire answer, right? Well, if your policy is optimal, why do you need this?
Your data set is slow to like technically one generate data set.
So your policy is not optimal, but your policy is like reasonable. You're saying you generate a better data set. Yes, yeah. So a lot of people they do start from like imitation pre-training and then like do fine tuning with something like RL. And so it's like it is much better to start from an imitation initialization than to start from scratch. Right. So it's a good question. Okay, so does it really work, right? And I think the important thing to think about is that what we did is we took this sequential problem and then we like threw away the sequential nature of the problem and then we pretended that it was a one-step problem, right? And because we pretended like it is a one-step problem, you're gonna accrue this thing called compounding, right? And so compounding error is how many people are familiar with compounding error? Okay, so let's think about compounding error, right? So compounding error says that, let's say, sorry, can you see my cursor? Okay, so let's say this is your training data set, right? This is your training trajectory. And what's going to happen is that I took like individual transitions and I said that I'm just going to try to predict the actions as well as possible on these individual transitions, right? And so if I was at that state, I would like have smaller than epsilon error on predicting the action. I'm trying to be good at predicting individual actions, but it's not zero, right? So you're going to have some small amount of error. And so what's going to happen with your small amount of error is that at the first step, you'll make a tiny error. Your tiny error will land you up in a state that's a little bit different than the state in the demonstrations, right? And now you've gone a little bit out of distribution. So you have like a function approximator, right? And this S is now a little bit out of distribution at the first time step, right? And so now you're a little bit out of distribution, so you're going to go even more out of distribution because your policy is not good out of distribution, right? So it's like if you have a training distribution, it's good in the training distribution, but it's not good out of distribution, right? That's machine learning doesn't guarantee that for you. So you made a little mistake, you're going to make a bigger mistake, you're going to end up somewhere else, right? Now you've gone even more out of distribution, so you're going to make a bigger mistake, end up somewhere else, right? And so oftentimes you'll see that the trajectories will start deviating from your expert data, even when you like replay the same thing, right? Just because of tiny, like from the perspective of one-step errors, they're like pretty small. But when you put them together, they become like a larger and larger error because you're getting to more and more out of distribution states. Right? Does that make sense? Okay, so when viewed from the like mathematical perspective, right? It's the objective that you're training is expectation of S star and A star from D, right? But the objective that you're evaluating, you train your policy like this, right? And then this policy is saying you train it on one-step transition. The way you're evaluating your policy is you're running your policy out in the environment sequentially, right? And so you're going to like evaluate your policy as something like this, right? So you're going to say like, this was sampled from a static data set, but the way you're going to evaluate it is you're going to like run your policy forward. Let's say rho is your like distribution of running your policy forward. So you run your policy forward, it's going to give you some states and actions, and then you're going to see, did I deviate from the expert or not, right? And the difference here is that the left-hand side is from the static data set, and the right-hand side is from the policy rolled out step after step after step. And so if you make a small mistake, like this thing becomes pretty different from this thing, right? And these are not the same. So your training and testing objectives are not the same, which means that like small mistakes at training, which seem okay for training, might be really bad for testing. So that's the issue. So the issue is that you're not training on the objective that you care about. The objective that you care about is that it's like rolling out the policy. And the reason RL is nice is because it trains on that objective. Whereas supervised learning trains on this other objective, which is a proxy for that, but it's not quite the same. Yeah. Yes.
So why don't you try to get closer to RL by instead of using single gate action pairs, why don't you just use a sequence of gate action pairs and then mark the log?
So it's not just about having a sequence, it's about having a sequence under your trained policy. So it's like, it's not just about the fact that it's a single tuple, you can even have a history. It's more about the fact that you're sampling under your learned policy. And so if you have to sample under your learned policy, then you have to like roll out in the environment. And so there are like better methods we'll talk about in inverse RL, which try to do exactly what you're talking about, which is try to do imitation learning, but not with this objective, with an objective that looks more like that. without rewards or anything still, but just using that objective. Right? But yeah, it's like this paradigm, there's nothing about it needs to be Markovian. Right now we're learning Markovian policy, which means it only depends on the current state. You can also do it on history. It'll still have the same letters. It'll in fact have worse problems. Yeah.
If you start on the right side, always just like assumes like it's like a you assume you're able to query the human or the expert, but in any state.
Well, you can do that. That's the interactive oracle assumption. You can also like assume that you have a static data set and you have to model the expert will do that. But it's like
That kind of reduces to this, right? No?
it doesn't reduce to that because you're still sampling under your policy. So you're going to say you want to sample under your policy, and you might want to say, hey, I don't know what the expert's going to do outside of what I've seen, right? But you're still saying I'm going to sample under my policy. So the important thing is you're trying to see like what would happen if I actually rolled out the policy versus like hope that it works if I like train on the static data. Okay. So the nice part about it is that it fails in practice as well, and this is not just a figment of my imagination. And so, this is some stuff from the former law. You can see they're like drifting all over the place because of compounding error. That's some stuff from Muchoko Tunalai, which is crazy. And then this is some stuff from Kay and Yunshu and others in our lab where they're trying to do behavior cloning for insertion. And it's like very similar to a training condition, but you accumulate tiny bits of error that make you fail at the problem. And so these things become important, especially when you're like doing high precision problems. Okay. So given that we believe that compounding error is a problem, let's start to think about what we actually want, right? So what we actually want is that let's define a cost function which says that the cost is 0 if the action is equal to pi star ST, that's the expert, right? And 1 otherwise, right? So it's saying that what you want to do is you want to ensure that the action you predict is as similar as possible to the expert action. And it's cost 0 then and cost 1 otherwise, right? And so what I'm trying to do is I'm trying to formalize like what is the best possible thing we can expect from imitation. So we want to formalize it as a cost. So we're going to say this is like a 0-1 cost. You can say the cost is 0 if you match the expert, cost is 1 otherwise. And what you want to do is you want to evaluate how good a policy is by measuring its expected cost when you sample from your policy by theta. And so you're saying, I'm going to sample from my policy by theta, and I want to measure its expected cost, which is the expected deviation from the expert, right? So this is exactly the same thing as like this thing on the right. Like those are the same thing, right? But the point here is that a policy, which is a truly expert good policy, is going to have 0 cost to it. So it's going to just like always match the expert. You're going to have 0 cost. And what I'm going to try and show is like how bad is behavior cloning. So if I choose a policy which optimizes this objective, I choose the best policy, and then I evaluate it with this cost, how bad is it? Right? So what we're trying to do is figure out how bad behavior cloning is. Yeah. Okay. So we're not going to get too much into the theory or anything, but we're going to just think about showing that behavior cloning has quadratically compounding error, right? And so the way to think about it is you can think of behavior cloning as kind of being on a tightrope, right? So it's saying that on these set of states, you're like good, right? As soon as you like miss them or you go off them, you're no longer guaranteed to be good. And so you can be arbitrarily bad, right? So it's like, as soon as you start going out of distribution, you can be arbitrarily bad. So you're on this like tightrope of states where you are good. And if you go off this tightrope, you fall, you're dead. And you incur maximal cost. Okay. And so the way to think about it is if you say that your policy pi theta has less than epsilon likelihood of deviating from the expert on these states which are in distribution, right? So it's saying this is saying that this is the likelihood that the action is not equal to the optimal action, right? So it's like saying, what is the likelihood that your policy is suboptimal? And we're saying it's less than epsilon on in distribution states, and it's arbitrarily bad on out of distribution states. And we're going to say, let's say we have a horizon H. The basic intuition for the proof is that if you fall off, like let's say you made a mistake somewhere, right? you're gonna assume that you've gone out of distribution, or like, if you make a mistake, you're gonna go out of distribution. If you go out of distribution, you assume the worst. You have a upper bound. And you say that you're just gonna like keep being bad for every state thereafter, right? So you're gonna say, okay, at every state, you have an epsilon likelihood of making a mistake, right? And if you make a mistake, then you incur all of the cost of the steps thereafter, because your policy sucks everywhere, right? It's only good on this tightrope. So it's saying at every step, you have an epsilon likelihood of making a mistake, right? And then you have a cost of H that you're gonna get, right? So let's say you made a mistake here, you're just gonna incur the whole cost. You made a mistake here, you're gonna incur H minus one. If you made a mistake here, you're gonna incur H minus one. Right? So at every step, you have a likelihood of making a mistake epsilon, and then you're gonna get approximately a cost of H, because you're assuming worst case where if you're out of distribution, your policy is gonna be arbitrary. Right, so what this means, if you take up epsilon H and sum it up over H terms, you get epsilon H squared, right? And so this is just going to be saying that your policy is bounded by epsilon H squared, which means that like your question about long horizon, right? It's like as H gets bigger, your error gets bigger. So it's saying that your expected cost for your error is going to grow with epsilon H squared. And that's bad. And so some of the algorithms we'll talk about try to bring it down. I don't want to go too deep into there's a simple proof here. I'll post them on the slides. So if you want to discuss them, come talk to me after. It's a little more involved, but essentially the idea is just like you try to get the likelihood that you make a mistake at every state, and then you incur the worst case cost after. Yeah. Yeah, that's short. I think what you do is like you do 1 minus epsilon to the T and good catch. Okay, any questions? So are you convinced that behavior cloning is garbage? It's upper bound.
Is there like a similar lower bound?
I don't think you can guarantee a lower bound in arbitrary environments, right? Because in some environments, you might just like always get zero cost.
But it's like relatively tight though.
Depends on the environment, right? And depends because it's the worst case bound, right? So we're like depends on the choice of function approximator in the environment, because we're saying okay, it's like arbitrarily bad here, so it's not clear that it's a tight bound. Yeah. Sure.
So yeah, I think the innovation learning was that we have a rollout, but we want to generalize it. And that's why we want to learn a policy. But we know that the moment we're out of that rollout, not in a phase from that rollout, we are going to do horrible things. So like, wouldn't we just use the rollout we already?
That's a good question, yeah. So what you want to do is you want to generalize in distribution out of sample, which means that you're able to generalize to new conditions which are drawn from the same distribution, but may not be exactly the same as training samples. I think what happens here is that you can end up out of distribution, right? So it's like, basically like when I say in distribution out of sample, maybe the easiest way to think about it is, like imagine that you had, this is your training distribution, right? And this is like what your training data set was, right? This is in distribution out of sample, this is out of distribution, right? And so it's saying that like this kind of thing is sending you out of distribution, whereas like let's say you like learn how to pick up the cup here and here and here and here, you should be able to generalize to picking it up here, because in distribution out of sample, right? Okay, yeah. Sorry, I actually said, isn't arbitrary solving it's not just the expert. Yeah, I guess this is like a supervised learning oracle, which says that if you train policy with supervised learning, the likelihood that you're like a not equal to is probably like you probably want to say like 1 minus phi of a. Right, so you want to write that as a probability rather than a not equal to, like a not equal to the shorthand. But if you think about this like as like maximum likelihood problem, it's like trying to quantify like what is the like likelihood of producing the expert action. Right? So it's saying the likelihood of producing the expert action is greater than equal to 1 minus epsilon. Okay. Okay, great. So now that we've been convinced that behavior cloning is not ideal, it's promising, but it's not ideal. Let's try to think about how we can fix it, right? And so in this column, there's two terms, right? There's epsilon, which is like the error, the likelihood of making an error in producing the optimal action, and then there's 8 squared. And so we're going to try and fix both of them, right? So we're going to call the thing that reduces epsilon underfitting, and the thing that fixes compounding error, or like quadratic growth, is, or we're going to call quadratic growth as compounding. Right? And so let's start by thinking about what does underfitting mean in imitation learning, and how do we like resolve this? Yeah. Do people want to break before we keep going? Be helpful, or keep going? Okay, keep going. Okay. Okay, so let's start thinking about underfitting and what this means, right? So intuitively, what this means is that in certain problems, that epsilon might be pretty large. And we're going to try and just understand why it's large and how we can resolve it. And so behavior cloning can underfit the data, right? What this means is that you're saying that epsilon is the likelihood that you are producing the wrong action for states that are in your training distribution, right? So I'm not saying go out of distribution. I'm not saying generalize. I'm saying for things in your training distribution, are you like producing things that are less than equal to epsilon? You may not be able to satisfy this, and that's what we're going to call underfitting, right? So a natural question to ask is, okay, can I just like make a bigger neural net and will it solve all my problems? And so like if scaling laws are to be believed, then we just need to make the neural net bigger, and then the loss will just keep going down, right? And so you know, a natural thing to do is just make the model bigger, right? So if the model is going to be bigger, then you're gonna, if it's universal, then you hopefully get the deal. And so hopefully that'll let us bring down the epsilon to arbitrarily small. Now, is this always true? And why might it not? Yeah.
You probably also want to like scale up data and something like that, otherwise might switch it over.
Yeah, definitely. Yeah, so you want to scale up data so you go to overfitting, but let's think about underfitting first. Good point. But my claim is that we will underfit even with the same data and a huge model. And so are there other reasons why that might happen? Yeah.
Is it because you're
Let's say we want to like take the error on that different objective, not even on the original objective. So let's not even measure the original cost. Let's just say supervised learning error doesn't go down enough. So why might that happen? No, it goes down. It doesn't go down to the level you want, right? For such.
much too sparse and sample part, so no matter what we train on.
Right. So generalization is more like Prana's point about overfitting and so on, right? I'm just thinking about underfitting. So let me get to it. I'll explain what I'm talking about. But when I'm thinking about underfitting, I'm thinking about before we get to this, I'm thinking about settings that look like this, right? So imagine that you folks see this. You have a setting that looks like this, where you have like an obstacle, and then you have half your demonstrations going this way, half your demonstrations going this way. Right? You have like a ton of demonstrations, a huge model, half your demonstrations going this way, half your demonstrations go this way. And then you try to, so like the action distribution looks like this, right? Multimodal. And then you try to fit it with the Gaussian. So no matter how big your neural net is and how much compute you pour in and how much data you pour in, like your Gaussian is never going to be able to fit a multimodal distribution, right? And so the problem is not about the expressivity of your function approximator, it's the expressivity of your distribution class, right? And so you can think of like different types of, like we talked about how policies are mappings from states or observations to distributions over actions. Right? They're not like scalar mappings, they're not deterministic mappings, they're mappings to distribution, right? So you can map, for instance, in a discrete setting, the states to a distribution over actions, or the logits for a categorical distribution, or for a Gaussian, you map from states to the mean and the variance of a Gaussian, right? Or for a diffusion policy, you map from states to the grad log pi, right? And so the point is that each of these are distributions, and if you choose an underexpressive distribution, for a more complicated policy, for more complicated data distribution, no matter how big you make the function approximator, it's never going to approximate. No matter how big you make your neural net that maps from the state to the mean and variance of the Gaussian, it's never going to fit a bimodal distribution. And so you want to just you don't want to just think about the expressivity of your function approximator, but also the expressivity of your policy class.
Yeah, distribution passing as policy class.
Policy class is really a combination of your function approximator and your like distribution class, right? Because your policy is a mapping from states to distributions of actions, so you need a function approximator and the choice of like probability distribution. Yeah. You see another question?
So that's right. Neural nets still softmax.
Well, okay, so a softmax would be something that looks like a database, right? And then a Gaussian is something that is a discrete probability distribution, there's a continuous. Right? So in a continuous space, a lot of people when they're doing behavior coding will do regression. And a regression just means they're doing Gaussian with a fixed there. That's what you're saying, you're going to do a Gaussian, and if you're doing Gaussian for multimodal data, you're going to like underfit the data. Now, the consideration looks different in a categorical, but in most robotics problems, for instance, you can't like discretize the space because you have torques and you have like an 8-dimensional space. And so oftentimes the tricky part is that, these things are extremely simple and tractable, very efficient. Log likelihoods are very easy to compute. Things like diffusion policies are not limited to Gaussian, right? Diffusion policies are like energy-based models or things like that. So they can represent like arbitrary distributions, right? But they come with tractability problems, like they hard to evaluate likelihood on them. It's hard to like, they're slow at inference, right? So there's a trade-off there. But the trade-off here is between computational tractability. So this is extremely tractable, Gaussian, very easy to compute. And this is like extremely expressive, but like less tractable. Right? And so you don't always want to use the like, if you're using a robotics application, for instance, you're trying to go very fast. It's a diffusion policy is far too slow. We want to be a little careful. Yeah.
Maybe you get here, but instead of taking a model that's expressive enough on the distribution, couldn't you make it so that the states are more correct? Like, for example, going up and going down is considered the same thing.
The states are more abstract or the
Like,
actions are more abstract?
Well, I guess my point is like, those both work as solutions. Perhaps abstract them into one thing instead of it, averaging.
I see. Yeah, so you could like have a hierarchical system where the like low level chooses to go up or down, but from the perspective of the imitation learning, it looks the same.
Perhaps.
Yeah, I think that would totally work, but you're maybe kicking the can down the road a little bit to like how do you get that low level thing that does the abstraction? So like if you're trying to get that low level abstraction from imitation, then you're like stuck with the same problem.
I guess like there's like, for it to come to the same solution, there's like some notion of similarity between those
Right,
paths. Could that be like found separately to make the problem easier for everybody?
I think it's good, but if you want to represent both paths, right, no matter what, then you have to like have something that is expressive enough to represent both paths at some level. Whether that's at the high level or the low level, somewhere you have to be able to represent two paths. Right?
Okay, I see.
Okay, so so the key point I want to get across is like, don't just think of this as a bigger neural net problem. It's also like you want an expressive enough distribution structure. And so the reason like diffusion policies and these kinds of things have made so much noise recently is because they like they make it kind of computationally tractable to have a much richer probability distribution. And that kind of lets you learn from more complex multimodal data. Right. That's why they're cool. Okay. So how does this reflect on imitation learning? Right. So if you have like same the thing I do here, you go left or if you go right, try to fit it with the Gaussians, and you're trying to do, it's a combination of the fact that it's a Gaussian and you're optimizing a supervised learning objective that's going to lead to more averages, right? So the point here is that if you have like a bimodal Gaussian and you're going to try and do supervised learning on it, you can show that a bimodal Gaussian with supervised learning is going to do averaging, right? And so we want to avoid this kind of averaging because the averaging is going to send you straight into the obstacle. And so if you try to fit it with a Gaussian and a supervised learning objective like this, then you would go straight into the obstacle. Does that make sense? Because you're averaging the modes, there's no way that a Gaussian can represent both. And the supervised learning objective doesn't allow you to drop any of the modes. It's a mode covering objective, which means that you get penalized for dropping any of the modes. So your supervised learning objective won't let you pick one mode or the other. It forces you to cover both. Right? Okay, so does this problem make sense? Are we parsing? Are we confused? Ask me any questions if you are. Okay, so the main thing we talked about is, okay, where your model is going to underfit in initiation learning because your distribution wasn't expressive enough when combined with the supervised learning. So that's the problem. What's the solution?
Expressive distribution.
Right, so it's a combination of expressivity and the objective, right? And so what you need to do is you need to like either change the objective so that you are okay dropping one of the modes, right? Or you need to make the policy more expressive. And so those are the two strategies we'll take to solve this. Right, and so let's try to take a little bit of a closer look at the objective so we can derive both of these things, right? And so the objective we written down is supervised learning, right? So it's the expectation of S star A star from D log pi theta A star given S star. What I'm going to try and do is trying to convert this into a divergence, and divergences are easier to analyze than like maximum likelihood. So I'm going to try and convert this into a divergence between different things, right? And so what we're going to see is that you can write this objective as an expectation. Let's kind of break this down step by step. So what I like my main point here is I'm going to try and convert this maximum likelihood objective into a divergence. Okay, so I'm going to try and write it as the divergence between something and pi theta, right? And so let's say that the distribution of the expert, the thing that you sampled D from was pi E, right? So let's say basically the distribution that you sampled D from was sampled from like P pi E, of S times pi E, this thing given S, right? So it's saying that like this is the distribution, this is the distribution of states in the expert, and this is the distribution of actions from the expert, right? Sorry, that notation was a little crappy. So we're going to say that the expert distribution is P pi E of S times pi E of A given S, right? And so that is the let's say that is the distribution of the expert. It's not known to us, but let's say that is the distribution of the expert, and D is sampled from that distribution, right? Let's see if I can come out. Then what we're going to say is that you can rewrite this expectation. Now, in terms of the fact that D is sampled from here, you can say that this expectation can be written as the expectation of S star from P pi E, which is saying that like sample states from the distribution of states that the expert visits. Yeah. And then you're going to sample actions from the expert policy. It's unknown, right? But we're trying to write divergence of unknown. You're saying sample actions from the expert. And then you say the objective is log pi theta. And because this is pi theta, I can just like add a constant to it, right? It doesn't matter. It doesn't change anything. I can add something that is independent of theta, and it doesn't change the objective, right? And so I'm just going to subtract minus log pi E of A star given S star. Right? So I'm going to say I re-express this thing as P pi E times pi E, right? From the definition of the expert distribution from this thing. And then I just added this, or like I subtracted this constant, right? Which is minus log pi. Yeah. Everyone with me? No. Okay. Let's rewrite that. So let's say you have let's say the data came from some expert policy file. Okay. Like we don't know that expert policy, but it's an expert policy. Now, when you run that expert policy forward, you're going to get state sample from P pi E of S. It's just like the distribution of states that you get when you run the policy forward. And then you're going to sample actions from pi E of A given S, right? So it's like, imagine you had pi E, you wanted to get an expert data set, you're just going to run the policy forward to get the state S, you're going to sample actions from pi E of A given S. Yeah.
Is the first one an initial distribution, or is it just like distribution in the number of states?
It's a distribution of states that you run the policy forward. It's like a station distribution. So it's saying you run the policy forward, you get a distribution over states, then you sample actions from pi E of A given S, right? So it's saying, okay, if you had an expert, the way you could re-express D as coming from a distribution where you sample from your expert policy, you get the expert states, and then you sample the expert actions using Python, right? And so the way you can think of obtaining D is that you just ran the expert policy in the environment. Does that make sense?
Series of limitations. These trajectories.
No, so like, this is a data set, right? It's like hard to express divergences in terms of a data set. And so what I'm saying is that, let's say that there existed a distribution, or let's say that existed an expert file, an expert made the data. Yeah, the expert made the data set, right? And the expert, let's call it phi E, right? And the distribution of states that phi E visits is phi E, and the distribution of actions is phi E given A given S, right? And so you can equivalently express an expert distribution E as sample from phi E, or you can like, if you had it, like the expert collected the data, right? So the way the expert collected the data is that they just ran phi E in the environment, right? And you can say that the likelihood of a state in action in your expert data set is equal to the likelihood that that state was reached by the expert times the likelihood that the action was taken by the expert. And so, okay.
They have max.
Well, I didn't know that kind of thing. I mean, you could do max or argmax. Yeah, the argmax is fine. Yeah, argmax is probably that. I wasn't careful. Yeah, because right now, I mean, we haven't said that this is equal to something, right? So if you're going to do that, you do argmax this, and let's see what it fits. Phi E does not visit all data points.
But like then like the this equation, like is it the same thing because top line is I guess that expectation of percent from some data that is by not the default.
So it's saying that the distribution D is coming from the expert, or the data set D is coming from the expert, and phi is the generating thing for the expert, right? And so it's assuming that you have an infinite size base, right? But it may not have visited all the states. But okay, I think we might have gone too deep into this rabbit hole. What I'm trying to get to is that I can just express this as a KL divergence, right? So what I'm trying to get to is that if I rewrite it this way, right, what I can do is I can rewrite this as, I can just say log pi minus log pi. You can write as log pi E divided by log pi theta from log identities, right? And so then you can write this as the expectation of states coming from the expert state distribution, actions coming from the expert policy distribution of log pi expert divided by pi theta, right? So all I did, so the steps we did is, this is supervised learning, maximum likelihood. We rewrote that sampling from that data set as sampling from the stationary distribution of the expert, right? You can just think of like, if you have an expert, getting a data set from the expert and sampling from the stationary distribution of the expert are the same thing. So what we did is we moved that to this expectation, and we just subtracted a minus log pi E, right? And then we just use log identities to convert it into this log pi E by pi theta. And so now what this looks like is, this is just the definition of a KL divergence. And so KL divergence, did you all do the knowledge quiz? Did everyone do the KL divergence question? That's fine. So I expect you to know what a KL divergence is. But a KL divergence is going to be integral P log P over Q, right? And which is basically expectation P log P over Q, right? And that is exactly this thing, right? And so it's saying that when you sample expert states from like whatever the expert state distribution is, you want to minimize the divergence between pi E, which is the expert, and pi theta, which is the thing you're trying to learn.
This may not matter, and I guess it makes sense because like, isn't it supposed to be pi theta divided by pi E?
I switched max and min. Yeah.
Oh,
Yeah. Yeah. Okay, so the point here is that we're trying to what I'm trying to do is I'm trying to convert that maximum likelihood problem into a divergence minimization problem with a particular form of divergence, and we'll talk about the properties of that divergence. So just to recap, I know this is a little bit confusing, it's new math, so let's make sure we get through it, right? Which is whenever you sample from an expert data set, all I'm saying is that sampling S star A star from the expert is equivalently saying that sample S star from the stationary distribution of the expert and sample A star from the expert false. So this is saying, this is sampling S star, A star from the expert. This is saying sample S star first from the stationary distribution of the expert and sample A star from phi E conditioned on the state that the expert reached. Yeah. Yes. Oh, yeah, like this also is equal to this. Yeah. The thing inside the distribution. So we just wrote this as sample S star from P pi E, A star from pi E, and then we just subtracted the minus log pi E because it doesn't change the optimus, right? And you made a good point, it should be argmax and not max. And then we just switch the max and the min, and you can rewrite this as A star from pi E log pi E by pi theta, which is the scale divergence between pi E and pi theta. Right, and we'll call this the forward KL divergence because it's the forward KL divergence is in the phi E is the first term and phi theta is the second term. Right, and so the reason it's important that it's the forward KL divergence and not the reverse KL divergence is because the forward KL divergence is mode coverage, right? Which means that, like, let's just try to analyze DKL pi E and pi theta, right? So let's say you had, let's say pi E was a bimodal distribution, right? And pi theta was a Gaussian, right? What you're going to do is if you look at this objective over here, you're going to be penalized if you miss anything that is sampled under pi E, right? So as soon as there is anything that is sampled under pi E, you're going to eat a penalty if it's not represented. So if you look at if there's something that is sampled under pi E, but it has extremely low likelihood under pi theta, you're going to eat a huge penalty. Right? Because it's going to be really low likelihood under pi theta, which means it's going to be huge when you do log of 1 over that. Right? So what it means is you can't fit something like this because you're just going to eat a huge penalty. So the forward KL divergence is mode covering because as soon as you drop anything that is in the first, that is high likelihood under the first term, you eat a huge penalty. Right? So you can think of it as you'd much rather do this because you're not eating a huge penalty anyway. Right? Does that make sense? So the reason that imitation learning has this underfitting problem is because it's doing the forward KL divergence. And the forward KL divergence is going to eat a huge penalty if it misses any modes. And so with the Gaussian, it's going to try and average the modes. Yeah.
So confused why our pi theta is necessarily a Gaussian here. Can't it have more expressive power? Couldn't it?
So let's say what would it be?
What do you mean?
What if it's not a Gaussian? What would it be?
I mean, can't we make it anything arbitrary we want? Can we output a whole vector of numbers and then say?
Well, that's not a probability distribution. So you want a tractable continuous probability distribution that is multimodal and easy to compute. So it's a big problem in generative modeling is trying to find expressive probability distributions that are tractable. Right. So there's things like energy-based models that are really expressive, arbitrarily expressive, but they're extremely difficult to compute and train because they're unnormalized. Right. So when you're trying to get tractable multimodal probability distributions, it's difficult to get those. That's why diffusion is a big breakthrough because it gives you an easy way to get multimodal probability distributions which are tractable. Right. And so a Gaussian is easy to do, right? Maybe a mixture of Gaussians is easy to do, but it's hard to get an arbitrarily expressive probability distribution that you can sample from and you can evaluate the likelihood from. That's the biggest problem in generative modeling. It's that's why you need GANs and normalizing flows and this, that. The issue is you need a tractable likelihood. And so it's hard to express a tractable likelihood for an arbitrarily expressive probability. That's it.
So does that mean that when we're talking about all models, instead of we're in deep learning, regular deep learning models, when you say softmax, we're instead going to the whole objective is predicting parameters for distributions.
Right. Even a softmax is a distribution over the outputs.
Yeah.
The reason we'll talk about something that looks like a softmax in a second. The reason the softmax is difficult in most RL settings is if you had a one-dimensional thing, it's usually a continuous action state. The softmax isn't applicable, but you can discretize. But let's say it's one dimensional, you discretize it in 10 bins, you're good. Let's say it was 10 dimensions. Right? Then you have let's say 10 bins per dimension, and then 10 dimensions, you have 10 to the 10 bins. So it's like a huge classification. So that's what makes it difficult. So it's like not tractable.
I see.
And so a softmax is nice in that it doesn't suffer from these things. It's very expressive. It doesn't like have mode averaging problems, but it's like tractability. So expressivity versus tractability.
Just to be clear, like, the output of the model then is just the mean and variance of a Gaussian.
In this case, yeah. So a lot of the RL repos you'll see, usually I'll put the mean and the log STD, so that it's like, because you don't want, like, the STD has to be positive. And so if you output the log STD, it's always guaranteed to be positive, but you'll output the mean and the log STD, rather than like arbitrary like probability density. So you output the parameters of a probability distribution. The newer things that we'll talk about your question in a second, we'll try to go to more expressive probability distributions. But there's like, it's not as trivial as it seems because of this like tractability versus expressivity. Okay. So the point I want to get across here is maximum likelihood is the same as the Ford-Tail divergence, right? Even if you didn't follow anything else, just remember maximum likelihood is the same as Ford-Tail divergence. Ford-Tail divergence eats a huge penalty if it misses a mode, so it tries to average the modes. Right? And so that's a big issue with the way most people will do like behavior cloning, and that's why it suffers from this like mode average. With me? Yes. Okay. Solid. So the Ford-Tail divergence is one divergence, right? But it's one divergence in a broader class of divergences, which we'll call F divergences, right? So an F divergence, more generally, is written as something like this, right? Which is the F divergence between two distributions P and Q is the expectation under Q of F of P divided by Q, right? And so it's saying that we can instantiate, for instance, the Ford-Tail divergence as a particular instantiation of an F divergence. But there's other divergences, right? So it's like if you instantiate F equal to X log X, you'll get the Ford-Tail divergence, right? Like let's derive that really quick. So an F divergence, just to make it clear, is like expectation Q F of P divided by Q. Let's set F to mine our X log X. Yeah, let's set F to X log X, right? So F of X is equal to X log X, right? And so like, let's take the F divergence and instantiate it with F is equal to X log X. Yeah. So what that's going to give us is the D of P comma Q is equal to the expectation Q of P over Q log P over Q, right? You instantiated F as X log X, right? And so we said F is going to be X log X. And so F of P over Q is going to be P over Q log P over Q, right? And so you write it this way. And now if you just simplify this, this becomes expectation P log P over Q, right? Which is the Ford-Tail divergence, right? So what I show here is that an F divergence, when instantiated with F is equal to X log X, is going to give you the Ford-Tail divergence. Yes? You kind of follow me? Now, that's not the only type of divergence there is, right? So what's a different type of divergence we can use, which might be better? Just we're going to try a more expressive class of probabilities, but before we do that, let's try to change the objective to make it work. Sad. Played myself. Okay. Yes, but it's going to be mode seeking if you do the reverse scale, right? So if you set F to minus log X, I don't think you remember that. That's good. If you set F to minus log X, then you get something that's mode seeking, right? So let's try and investigate what's going to happen if you set F to minus log X, right? So if you set F to minus log X, your F divergence becomes expectation Q of minus log P over Q, which is equal to expectation Q log Q over P, right? Which is it's the KL divergence with just P and Q flipped, right? So it's just going to be DKL of Q comma P rather than P comma Q, right? So the nice part about doing the reverse scale divergence, remind me of your name? Pavel. Okay, as Pavel was saying, it's mode seeking, right? So it's, and when I say mode seeking, the nice part about the nice part about the reverse scale divergence is notice that the expectation is under Q. So let's compare these side by side, right? So we say, let's compare the forward KL divergence, which is expectation P log P over Q, and the KL reverse scale, which is expectation Q log Q over P, right? So this one is under P and this one is under Q, right? And so we said that, okay, if P is our data distribution, the expert distribution, and Q is our learner, then we really eat a huge penalty for missing something in P, the forward scale, right? So that's why we're mode covering. But in the reverse scale, you're sampling not from the data distribution, you're sampling from your own policy. You're sampling from Q, which is the learner. So you're like not going to eat a huge penalty for dropping a mode. Right? So you're gonna like say, okay, like if I don't care about a mode, I just set it to be low likelihood and I don't need a huge penalty for it, which means that the reverse scale divergence seeks a mode, tries to find one, right, rather than covering them. So the forward scale is mode covering and the reverse scale is mode seeking, right? And all that we could write these both as F divergences between the expert and the learner by E and by theta. You just change the F, that's it. Does that make sense? So all of our like convoluted math, all of the, oh no. All of our convoluted math is really to get at the point that imitation learning is minimizing the divergence. It's minimizing the forward scale divergence. Forward scale divergence is mode covering. If you change it to a mode seeking scale divergence, then you can like you don't have this averaging issue. Right? So the way that it'll work for this thing is that you would pick to go up or down. Right? You don't have to cover both. You're not going to go. Okay, so this seems like wonderful and great. Like why is it hard to do? Like why is this not the solution to like all of life's problems?
Because it doesn't come from the actual learning objective, which is S star, A star, ascending.
Okay, yes, that is definitely a problem. That is definitely a problem. But before we even get there, it's really hard to use that reverse scale. But
Because you need to sample from your learned policy and you need your optimal actions for states that you would reach by running your policy.
so notice that the objective that I'm talking about is S star still sample from the expert, and you just change the divergence on the actions. So you're not changing the states at which you're evaluating them. You're just changing the like action distribution, right? And so it's not like you have to go to different states, but it's very close to what you're saying. The tricky part is that the reverse scale divergence, right? So my Zoom is freaking out. Give me 1 second. I don't know how to get rid of the drawing. Okay, you guys might have to deal with the drawings. Because it refuses to go away. Okay. But the reverse scale, right? The challenge is that it requires expert likelihood. So if you look at the reverse scale, right? The forward scale was expectation pi e of log pi e by pi k, right? And so the forward scale says you have expectation pi e of log pi e by pi theta, right? And this log pi e doesn't really affect anything, right? And so you can throw it away. And so you get expectation pi e of minus log pi theta, and that is maximum likelihood. And we're all good because you just need to be able to sample actions from the expert, right? And so you're good because you need to sample actions from the expert, but you don't need likelihood from the expert. You just need to sample from the expert. And that's the same as like collecting data from the expert, right? So it's easy to evaluate the forward scale because you just need a sample from the expert. The thing that becomes tricky with the reverse scale is that you need to know the likelihood of the expert, right? And the reason you can't just like throw it away like we did in the other case is because the expectation depends on pi theta, right? So that means that if you write this reverse scale as expectation pi theta of log pi theta minus log pi e, right? This thing actually does affect the objective. It's not like you can just like throw it away, right? Whereas in the other case where you wrote expectation pi e of log pi e minus log pi theta, right? Like this term is basically like a constant, it doesn't affect it, right? And so you can like throw that away. Whereas in this term, because the pi theta is in the expectation, you cannot throw away the log pi e term. Right? And so the tricky part here is that the reverse scale is tricky to use because you need to know pi e. So when you have like the setting that we talked about is we have expert data, right? Someone comes and demonstrates things to you, which is great, right? And you know samples from the expert, but you don't know pi. Right? And so that's what makes the reverse scale hard to use, is that you need to know the expert likelihood pi. And that's the thing that it's about. Okay. And so fortunately, one of my students, Kay, and her other advisor, Sid, had a great paper few years ago on trying to make this tractable. So let's recap where we are. We're underfitting in invitational learning. Because we're using the forward scale divergence of the Gaussians, we want to not underfit, we want to do mode seeking, so we're going to flip the forward scale to the reverse scale. Problem with the reverse scale is that you need to know expert likelihood. You can't just use samples, you need to know the likelihood of the expert. And that's like much harder to do than just like demonstrating expert. And so what Kay and what Kay and Sid showed is that you can convert this like intractable thing because you don't know the expert likelihood into a sample-based estimate that looks like a GAN. And so we're not going to go into the paper in detail right now, but you can think of it as like what Kay and friends showed is that you can take this thing that requires sample estimates of pi e and convert it into a GAN-like objective that the thing that requires known likelihoods and convert it into a GAN-like objective that only uses samples. So that's what makes her objective really cool, is that it gets this mode seeking behavior that you want, but it does it by just trying to convert it into a tractable objective, like something that you can just get from samples. I think that's why her paper is really cool. So you should go read it. So just to recap what we've done, forward scale is bad, mode covering. Reverse scale is good, mode seeking, but it's hard to optimize, it's hard to evaluate because you need to know pi e, and no one knows pi e. You don't know the expert likelihood. And you only have samples from the expert. And so Kay's method tries to convert that into tractable optimization. We're not going to get into the details of it. But yeah, I think that's what makes it cool. All right, more on this on Tuesday. Thank you.
What is the problem? Yes, we have like for engineering, fantastic descriptor where we divide that into different.
That would not be solved.
Yeah.
But then your data is not multimodal
uh,
because your state includes that system.
yeah, that's like, I guess in like, when we do big into, we use the task descriptor, yeah, like.
Yeah. A lot of in your problem, it's not a problem because you're discretizing the action space.
Oh, yeah.
And so that's why this goes. And we'll talk about why it's not a great idea. Not always a great idea.
Yeah.
But I think the way you're doing it is sensible and you'll discuss it.
There's a step where you have kind of like the arbitrary, like minus,
Yes.
whatever.
Yeah.
You can add like a plus, like, or whatever, like you can. Why is that reasonable to add?
Because it doesn't change the optimum.
But it's just like very convenient that it just like gives you like the forward KL, right?
Well, I did it to get the 4KL, but generally, if you have an optimization, you add
Right,
it, it doesn't change the optimum.
But I guess what I'm saying is like if you instead of like adding like the minus, you were to add like the plus, like whatever, then you don't get KL.
You don't have KL.
But it's still like the same optimization.
Same objective, right? But what I'm trying to do is convert it into a divergence, right? And so we're trying to show that it's equivalent to minimizing a divergence.
So that I get. I guess like what I was stuck up on is like, if you were to change it to something else, would you change the form of the KL divergence? Like, is there a way to make it so that instead
When you
of-
have log pi plus log something else, it's not clear what it is.
Right, yeah,
So I don't really know what those.
okay, yeah. Do they derive this whole thing in the paper?
Yeah.
Like, okay, I should go read
Yeah,
that.
it's a very good paper.
Yeah.
You should read it.
I was thinking it's good for like a tutorial. It'd be.
Absolutely, yeah. You should ask Kay, our very own to teach.
Yeah. Thank you.
Yeah.